Hi all. Today I am going to discuss the topics such as Wacker oxidation, Baeyer-Villiger oxidation, selenium dioxide based allylic oxidation and the ozonolysis. First, let's look what's Wacker oxidation. Wacker oxidation, it refers to the transformation of a terminal or 1,2-disubstituted alkene to a ketone through the action of palladium, catalytic action of palladium, water and a co-oxidant. The variants of this reaction will yield aldehydes or allylic or vinylic ethers and allylic or vinylic amines. Because of the ease with which the terminal alkenes can be prepared and due to the versatility of the methyl ketone group installed by the reactions, the Wacker oxidation, it has been employed extensively in organic synthesis. This chemical reaction, it was one of the first homogeneous catalysis with organopalladium chemistry applied on an industrial scale. Here it shows the general scheme of the Wacker process, that is a ketone being converted to an alkene being converted to a ketone in the presence of oxidation. Now let's discuss the mechanism of Wacker oxidation. The mechanism of Wacker oxidation, it has been studied both experimentally and theoretically. The first step, it involves the coordination of the alkene to the palladium center to form the pi complex. The evidence for this step, it is provided by the relative sluggishness of the electron-poor alkenes, which generally require the higher catalyst loadings than the unactivated alkenes. The hydroxypalladation, it then occurs to yield either the zwitterionic complex, that is the complex 3, or the neutral complex 4, depending upon the mode of hydroxypalladation. That is, at low concentrations of the Cl- ions, the syn hydroxypalladation appears to be happening, that is water coordinates to the metal and migratory insertion of the palladium OH bond occurs to generate the fourth complex directly, while at higher concentrations of the chloride ion, chloride competes with the hydroxide for binding at the palladium, and thus anti-hydroxypalladation will occur. Now, next, the beta hydride elimination occurs to afford the fifth complex, which then reinserts into the palladium hydrogen bond to give the sixth complex. The computational studies, it supports the involvement of the chloride assisted deprotonation in the subsequent steps, which afford the product and palladium 0. The oxidation of palladium 0 in the presence of copper 2 it occurs, which regenerates the palladium 2 series, that is the first same as the reactant. However, the role of copper 2 in the mechanism, it is poorly understood in this mechanism. The mode of hydroxypalladation, it is an important issue for the Wacker oxidation. That is, the hydroxypalladation, it can occur either in a syn fashion or in an anti fashion. If it is happening through syn, then an inner sphere mechanism is taking place, and in the case of anti, there is a nucleophilic attack on the coordinated alkene. Although the stereocenter in the fourth complex is ultimately destroyed by the elimination, the mode of hydroxypalladation, it can influence the site selectivity of the reaction. That is, Markovnikov type of addition of water to the more substituted carbon of the alkene, it forms methyl ketone, while attack of the water at the less substituted position ultimately yields an aldehyde. Thus, the mode of hydroxypalladation, it has been shown to affect the distribution of ketone and aldehyde products, and is also an important in the stereoselective Wacker cyclization reactions. Now let's look the Baeyer-Villiger oxidation. The Baeyer-Villiger oxidation of ketones, it is the transformation of ketones into esters and cyclic ketones into lactones or hydroxy acid in the presence of peroxy acids. A wide range of oxidizing agents can be used for the same, such as the peracetic acids, etc. The reactive or strained ketones, it reacts with the hydrogen peroxide to form lactones. Now let's look the mechanism of the Baeyer-Villiger oxidation. In the first step, what is happening is that the protonation of the carbonyl, it creates a reactive nucleophile, that is the percarboxylate. And in the second step, the nucleophilic attack on the carbon with the electrons from the C double bond or pi bond, it is going to the intermediate, it gives the intermediate. And in the next step, what's happening is that the return of the electrons from oxygen to reform the carbon oxygen double bond and the migration of the carbon electrons to form a carbon oxygen bond, displacing the carboxylate as a leaving group. And in the fourth step, what is happening is that the electrons from the carboxylate attacks the proton, resulting in an acid-base reaction which gives the ester and carboxylic acid as the results. The major applications of Baeyer-Villiger oxidations are: it has great synthesis utility as it permits the transformation of ketones into esters. Then an oxygen atom inserted to the carbonyl group. This reaction is applicable both cyclic and acyclic ketones. The oxidation of cyclic ketones occurs with ring expansion and it forms lactones, as in the conversion of cyclohexanone to lactone. Now let's move to the selenium dioxide based allylic oxidation. The selenium dioxide based allylic oxidation, it is called the Rayleigh oxidation. It means it is a selenium dioxide mediated oxidation of methylene groups adjacent to the carbonyls. That is, the selenium dioxide mediated oxidation of the methylene groups to alpha ketones at the allylic position of the olefins. It is shown by this equation, that is the oxidation taking place. Now let's see the mechanism of selenium dioxide based allylic oxidation. The oxidation of a reactant is studied. The oxidation of the carbonyl alpha methylene positions, it begins with the attack of enol tautomer at the electrophilic selenium center, and then it follows a rearrangement and a loss of water, which gives the equivalent of water attacks in the alpha position. Then the selenic acid is liberated in the final step to give the 1,2-dicarbonyl product. The allylic oxidation using selenium dioxide proceeds through an ene reaction at the electrophilic selenium center. And now let's look the stereochemistry of the selenium dioxide based allylic oxidations. The selenium dioxide, it is the most reliable and predictable reagent for this transformation, particularly for the more substituted alkenes. A number of studies have been carried out for the same. That is, we can see that the selenium dioxide, it produces unrearranged allylic alcohols, that is an ene reaction 2,3 sigmatropic rearrangement sequence being the probable major pathway. And while several methods for the oxidation of allylic carbon hydrogen bonds to produce alcohols are now available, which is based on the selenium methodology. Several studies have been carried out, and the studies serve to indicate that the complexity of this reaction and the difficulties observed in predicting the regio and stereochemical outcome. Apart from the allylic alcohols, other possible products are the dienes, esters, ethers, enones, alpha diketones, and the glycols. Under conditions of refluxing wet dioxane solution and a deficiency of oxidant, the obtained mostly unrearranged allylic alcohols, although the enones were also observed in some cases. And in contrast to the works, they have also suggested that the tertiary positions, they are preferentially oxidized over the secondary, and the secondary positions over the primary. That is, tertiary, secondary and primary will be the order. Then they further found that the reactions to be stereoselective pseudoaxial alcoholic products being favored in the cyclic systems. As you can see in this equation, the pseudoaxial alcoholic product is the more favorable one with 41%. It has early proposals concerning the mechanism of selenium dioxide allylic oxidations. It involved the solvolysis of allyl selenic acid intermediates or the free radical processes. A more complex picture was painted when the indicated that both the mechanism and reactivity sequences are dependent upon the alkene structure and the reaction conditions. But the fully regio and stereospecific sequence consists of the two consecutive pericyclic reactions, that is anene reaction followed by the sigmastropic rearrangement and the subsequent selenite ester hydrolysis. The applications of the selenium dioxide mediated oxidation, it was used in the synthesis of diterpenoid ranadol and in the axis of ingenol. Now let's look the ozonolysis. Ozonolysis, it is an organic reaction where the unsaturated bonds of alkenes or alkynes or azo compounds, they are cleaved with the ozone. The alkenes and alkynes, they will form organic compounds in which the multiple carbon-carbon bond, they will be replaced by a carbonyl group, and while the azo compounds will form nitrosoamines. The outcome of this reaction, it depends on the type of multiple bond that is oxidized and the workup conditions. It is an example showing the oxidative cleavage of a carbon-carbon double bond, which on the presence of ozone gives two ketone molecules. The ozonolysis of carbon-carbon double bond, it takes place through various ozonide intermediate followed by the workups in the formation of the respective products. The workup in the ozonolysis, it is divided into three categories. The first one, it is the reductive workup using mild reducing agents such as the dimethyl sulfide or the triphenyl phosphine or zinc dust, which produces the oxidation of the double bonded carbon. It on the presence of ozone, it will form an intermediate ozonide product, which on the mild reductive workup, it yields an aldehyde and ketone. The next case is the reductive workup using the strong reducing agents such as lithium aluminum hydrogen hydride or sodium boron hydride. The same process, it forms an intermediate ozonide, which on further strong reductive workup on this reducing agents, it will give alcoholic products. The next one is the oxidative workup using the oxidizing agents such as hydrogen peroxide or oxygen. It will also provide an ozonide intermediate, which on further oxidative workup in the presence of the oxidizing agents will yield carboxylic acid and a ketone. Now let's look the mechanism of this ozonolysis. First, the ozone inserts to the alkene by the 1,3-dipolar cycloaddition to form the primary ozonide, which is unstable, and it again undergoes the retro 1,3-dipolar cycloaddition to form a carbonyl and carbonyl oxide products. Then the carbonyl oxide it will which it is has a dipole which undergoes once again to form with the 1,3 dipole dipolar cycloaddition reaction with the carbonyl to form the stable ozonide. Then the next one is that the stable ozonide, it reacts with the reducing or the oxidizing agents to give the desired products. Thank you.